Today's video is on operation of signals using both dependent variable and the independent variable. As can be seen, the operation of signals is going to be discussed considering two aspects. One is the dependent variable and the second aspect is the independent variable. Considering the dependent variable, various operations are going to be considered, namely amplitude scaling, addition, multiplication, differentiation and integration. And the like. Let us go on to consider each of the operations in detail. Let us assume that x of t is the input and y of t is the output, as is the usual assumption for most of the signals problems. Amplitude scaling would be given by y of t is equal to c into x of t, where c is a scaling factor. In a discrete case, it would be represented as y of n is equal to c into x of n. Example for that is an amplifier, where if we give a signal of amplitude 2 volts, if c is equal to 2, output voltage would become 4 volts. Addition of signals could be considered by considering two inputs x1 of t and x2 of t, and the output y of t would be equal to summation of x1 of t plus x2 of t. Extending this to the discrete case, y of n would be equal to x1 of n plus x2 of n. Example for addition of signals would be an audio mixer which mixes music and voice signals. Next is an operation on multiplication of signals, where if we have two inputs x1 of t and x2 of t, the output y of t is going to be equal to x1 of t into x2 of t. In the discrete domain, it would be y of n would be equal to x1 of n into x2 of n. Example for multiplication is an AM radio signal, where x1 of t is an audio signal with DC component and x2 of t is a sinusoidal signal called the carrier wave. These two are multiplied to get the radio signal. Next we go on to two other operations, namely differentiation and integration. Considering the differentiation, let us consider that the input variable is x of t and output is y of t, as is the normal case. Hence, y of t would be equal to d by dt of x of t. And for differentiation, the example would be an inductor, where if we have an inductor of value L, we could see that if a current I of t passes through it and a voltage of V of t exists across the inductor, V of t would be equal to L into d by dt of I of t. Considering the operation of integration on similar grounds, integration with respect to time t gives output variable y of t as y of t would be equal to integration minus infinity to plus t x of tau d tau. And considering the example of integration, the best example would be a capacitor, which we are familiar in electric circuits. A capacitor is shown here, which has a voltage V of t across it and a current I of t flows through it. So V of t would be equal to 1 by c integral minus infinity to t I of tau d tau. Let us go on to consider these things by considering some basic problems on operation of signals. The first example is going to be a problem where x1 of n is given and we are asked to find out y2 of n, which is going to be 2 into x1 of n. It is a very simple problem because x1 of n is 0, 0, 1, 2, 3, 0, 0, 2, 2, 0, and y2 of n would be 0, 0, 2, 4, 6, 0, 0, 4, 4, 0, which is exactly what is going to be. Without even considering the figure, we can do it from the value of the sequence itself. So considering the sequence also, the same thing has been represented, where at -2 and -1 it is 0, at 0 it is 2, at 1 it is 4, at 2 it is 6, at 3 and 4 it is 0, and at 5 and 6 it is 4. The next is a problem on addition of two signals. Here, two signals x1 of n and x2 of n are given, and it is asked to determine y1 of n is equal to x1 of n plus x2 of n. Let us now try to understand the two signals. x1 of n is 0, 0, 1, 2, 3, 0, 0, 2, 2, 0, and at n equal to 0, the value of the signal is 1. Let us consider x2 of n. It is 0, -2, -2, 2, 2, 0, -2 and 0, which means at n equal to 0, the value of the signal is, as can be seen, 2. The addition could be better understood by considering the value of the signal, which is again clearly written at the bottom. Now let us try to see what happens. At n equal to 0, x1 of n is 1 and x2 of n is 2, giving y1 of n is going to be equal to 1 plus 2, which is 3. At n equal to 1, x1 of n and x2 of n are 2, giving the value 4. At n equal to 2, the value of x1 of n is 3 and 0 for x2 of n, giving the value of y1 of n as 3. At n equal to 3, x1 of n is 0, x2 of n is -2, giving the value of y1 of n as -2. And at n equal to 4, both the values are 0, giving the value 0. At n equal to 5, 6 and 7, only x1 of n is present, hence the values for x1 of n are repeated, which means 2, 2, 0. And let us go on to the negative side of n. At n equal to -1, the value of x1 of n is 0 and x2 of n is -2, giving the value -2. At n equal to -2, the value of x1 of n is 0 and x2 of n is also -2, giving again the value of -2. x2 of n exists at n equal to 3. At n equal to 3, x1 of n is not defined, so y1 of n is just 0. Hence, we get the answer as y1 of n is 0, -2, -2, 3, 4, 3, -2, 0, 2, 2, 0, where at n equal to 0, the value of the y1 of n is 3, as can be also seen from the graph. All these values are traced. Let us consider the next operation, which is going to be multiplication of signals. Here, two signals x1 and x2 of n are given, which is as defined in the previous case, and it is asked to determine y3 of n is going to be equal to x1 of n into x2 of n. x1 of n is 0, 0, 1, 2, 3, 0, 0, 2, 2 and 0. With n equal to 0, the value of the signal is 1. Similarly, for x2 of n, it is 0, -2, -2, 2, 2, 0, -2 and 0. At n equal to 0, as can be seen from the arrow, the value of the signal is 2. On observation, it is seen that the multiplication gives non-zero values only at n equal to 0 and at n equal to 1. At all other values, the value of the signal of either x1 of n or of x2 of n is 0, resulting in a 0. Hence, let us see what happens when n equal to 0. At n equal to 0, the value of the signal of x1 of n is 1. Similarly, x2 of n is 2, giving the result 2. At n equal to 1, x1 of n and x2 of n are 2 respectively, giving the value 4. This tells us how multiplication works. Let us now consider the operation of signals considering the independent variable. The various operations which we are going to consider in this case are time scaling, reflection and time shift. The operation that we are considering here is time scaling. Time scaling is applied to the usual input x of t and output y of t. Hence, the expression becomes y of t is equal to x into at when we scale the independent variable t. This results in two sets of operations. One is expansion of the signal, the other one is going to be the compression of the signal. Expanded version of the signal exists when a lies between 0 and 1, and compression of the signal exists when a is greater than 1. Let us try to understand this by considering the figure shown near. The signal exists between 1 to -1, which is going to be a triangular wave, and its amplitude is 1. We are considering expansion process where a is going to be equal to 1 by 2, or a is going to be equal to 0.5, which is less than 1 and greater than 0. Hence, y of t is going to be equal to x of t by 2. This results in a signal getting expanded between 2 and -2, which was originally between -1 to +1. The second example is the compression example, where the compression happens for a equal to 2, and here the signal gets compressed. The values which were in the time domain as -1 and 1 now become -half and +half. Next, let us try to consider the problem on time scaling in a more elaborate way. In the first case, it is compression which is happening for a equal to 2, and the signal x of t, as can be seen from the graph, exists between 0 to 1 in the positive case and 0 to -1 in the negative case. That means for t between 0 to 1 and between t equal to 0 to -1, the amplitude of the signal, as can be seen, is 1. During time scaling, the amplitude of the signal does not change. Hence, the amplitude remains at 1. However, compression happens only in the time axis. So, since a is equal to 2, it gets reduced by half, which means the value of the signal in the time axis gets reduced from 0 to 1 to 0 to half in the positive time axis, and in the negative time axis, the value between 0 to -1 gets reduced to 0 to -half. Let us consider the second case where expansion of the signal happens, and this happens when y of t is equal to x of t by 2, because the previous case was for y of t is equal to x of 2t. What happens when y of t is equal to x of t by 2? It is clear that when a lies between 0 and 1, expansion of the signal happens, as can be seen from the previous slide. So, the signal which exists between -1 to +1 now exists between -2 to +2, as is evident from the graph. The time scaling is also shown for a discrete case where y of n is going to be equal to x of 2n, and it could be seen that the graph shows that the value of the signal at n equal to 0 is 2, at n equal to 1 and 3 it is 1 respectively, at n equal to 2 and 4 it is 2 respectively, at n equal to -1 and -3 it is 1, and at n equal to -2 and -4 it is 2 respectively. What happens after time scaling? If time scaling happens with a factor of 2, as can be seen here, that is y of n will be equal to x of 2n. So, intermediate signals are removed, which means a compression of the signal happens, as can be seen in the first case, and when compression happens, the values of the signal at 1, 3, -1 and -3 are removed, and only the values at 2, 4 and -2 and -4 are retained, and they are shifted to 2 is shifted to 1, 4 is shifted to 2, thus giving the signal an appearance such that at n equal to 0, the value of the signal is 2, at n equal to 1 and 2 also, the value of the signal is 2. Similar thing happens on the negative axis, where the signals at n equal to -1 and -3 are lost, and only signals retained are as -2 and -4, which become shifted to -1 and -2 respectively. Reflection of a signal. The reflection is going to be defined as if an input x of t is given and an output y of t is given, reflection would be y of t is going to be equal to x of minus t. This reflection is quite evident from what is shown in the figure, where a signal exists between minus t1 to plus t2. Minus t1, from 0 to minus t1, the signal is shown in blue, and from 0 to plus t2, the signal is shown in pink. Reflection is just about the time axis. So what exists between 0 to t2 is now shifted to 0 to minus t2, and what existed between 0 to minus t1 now becomes 0 to plus t1. This is quite evident from its definition. Y of t is equal to x of minus t. When reflection is applied to even signals, there is no change because x of t is going to be equal to x of minus t. However, for odd signals, we recall that the definition of the odd signals is x of t is going to be equal to minus of x of minus t. Hence, this results in negative of the reflected version. It is also true for discrete signals. Let us now consider the example for the discrete case, which has been shown here as y of n is equal to x of minus n, and we could see that the values exist at 0, 1, 2 and 3, and at minus 1 and at minus 2. After reflection, the values which exist on the right side of n equal to 0, that means at 1, 2 and 3 are shifted to the other side, which means it becomes equal to minus 1, minus 2, minus 3, and the signals which existed on the left side of 0, which is at minus 1 and minus 2, now get shifted to 1 and 2. There is no change in the amplitude of the signal. The next discussion is on the next operation, namely time shifting. Here, when the input is x of t and the output is y of t, the time shifted version is given by y of t is equal to x of t minus t naught. This results in two cases, that is, when t naught is greater than 0, the signal is shifted towards the right, and when t naught is less than 0, the signal is shifted towards the left. Let us try to understand this by considering the example given here, where a square wave exists between 1 and 2 with an amplitude of 1, which is given as x of t. Y of t is going to be shifted by 2 units. That means it is going to be shifted as x of t minus 2. T naught, as can be seen, is a value greater than 0, which means it is 2. Hence, the starting point, which is at 1, would become 3, and the ending point, which is 2, would now become 4. For the time shifting case, let us consider the second example, which means at t naught is less than 0, what happens when the signal gets shifted? The value given here is t naught is going to be equal to minus 2. The signal given is x of t is a square wave which exists between 1 to 2 with an amplitude of 1, which was the same signal given in the previous case. So what happens? What happens is that the first thing that is considered is, because t naught is going to be equal to negative, that means it is minus 2, the signal is going to get shifted towards the left. Since the shift is negative, so it considers the shift for minus. The second is the value of the shift is 2, which means the signal shifts from 1 and it goes to 0, and finally it settles to minus 1 because the shift required is for 2 units. So the signal is going to be from minus 1 to minus 2, as can be seen in the graph. Now let us try to understand whether we have understood the concepts by considering quiz questions. One of the problems given is the output y of n is going to be equal to x of n plus 4. This represents reflection about the time axis, scaling, time shifting when n is greater than n naught, or time shifting when n is less than n naught. Here n naught actually represents t naught. Since it is n plus 4, it is understood that time shifting occurs for n less than n naught. The second problem is a figure is shown and it is asked whether the signal is going to be scaling for a greater than 1, reflection about the time axis, scaling for a less than 1, or whether it is going to be time shifting with t less than t naught. It is clear that it is x of t and the other value is going to be x of t to t, which means it is a scaling operation, time scaling operation for a greater than 1. These are the answers for the quiz. That is, time shifting happens when n is less than n naught. That is, in that case, n naught is going to be equal to minus 3, and in the second case, a is going to be equal to 2. References are given here.